All right, excellent. We've got people on. Beautiful, excellent. And I do have the closed captioning going on down on the bottom. It's not going to be perfect, but it should do pretty well. So it's nice to see everybody today. Hopefully everybody can hear through just the regular audio here. And I'm just going to make sure that we're all set here. Looks good on this end. All right, we've got 3 people connected to the 3 people connected to Pear Deck, which is phenomenal. Hey, can you guys hear me? Just want to make sure. All right, I'm going to check with Brianna. Hey, Brianna. Yeah, okay. As long as y'all can hear me. I love this. Some of you I recognize, which is really nice. Always love that you guys are here. Hey, I've got 3 o'clock right on the button. So let's go ahead and get started. And what we'll do is we'll just keep putting the Pear Deck link in. So I'm going to take a link here and I'll put it in the chat. And then Brianna, if you want to go ahead and copy that link and keep putting it in the chat every once in a while for people that come in, that would be awesome. Here we go. So this is on circular motion and gravitation, and I'm going to get rid of the graphics that are there because we don't need it anymore. And this is circular motion and gravitation. Just want to go through and talk about just a couple things, and we're going to get you active and have you go through and give some answers and do some things like that. So one thing that I need to let you know is the stream is being recorded, and it might appear on our website, YouTube, or other public channels. So if you ask a question, your name might appear on the screen. And if that does, just know that it'll be there. So if you want to change your name, you certainly may. Don't forget, keep promoting Think Fiveable. So do that on Twitter, Instagram, YouTube, those type of things. Hopefully we'll just keep, increasing numbers here. Really, really love all the things that are going on and all the great things that Fiveable's trying to offer for students. Going to get you ready for the big AP exams here coming up. Don't forget that on March 26th, that would be this upcoming Friday night at 7 p.m., we're going to go through energy. And then the following week, we will be taking a look on Saturday at momentum on April the 3rd. So hopefully we'll see you all there, and we can do a lot more review. Things that we're going to talk about in this stream: what's important when we travel in a circle. We'll think about corners. We're going to talk about centripetal force, apparatus, and what it is and why that's pretty important. How you behave on a roller coaster, or what you feel like on a roller coaster. And then we're going to take a look at the flying pig, talk a little bit about what's important about universal gravitation. And then finally, we're going to end up with satellites and speed. And if we have a little bit of time, we will actually play a little bit of Gimkit. That'll be kind of fun. So here are some things that you really badly need to know when you go through and you think about the important equations that you'll need for circular motion. So the first one is an equation that's kind of on the equation sheet. It is the change in position, or more of a distance, I think, than anything else, around a circle. So what we're going to do is anytime you need to get on the AP Physics 1 equation sheet, it's easiest just to go to Google, type in AP Physics 1 equation sheet. When you do that, the very first link there will bring up that equation sheet. I'm going to make it a lot bigger so that you can see. And don't forget that in addition to all of the physics equations, there are also geometry equations over here on the right side. So you'll notice that for a circle, if we want the path around a circle, we can use 2 pi r. And that's where this 2 pi r comes from. And that is just the change in position along the circle. So if I want the speed in a circle, remember the velocity or the speed in a circle is equal to 2 pi r over the period. So be really careful with this equation because this is instantaneous speed. I guess you could kind of think it that way. The speed at a particular position would be more or less the velocity. If we're thinking about the straight line velocity for a circle, that's really called tangential velocity. And so that's kind of where this comes from. The acceleration in a circle is v squared over r, where v squared is this tangential velocity that we have there. That equation is on the equation sheet. So if we back up and come back over to the equation sheet, you'll see that it is AC is equal to v squared over r. And so hopefully that's super helpful. Let's go back to the presentation again. The last equation that's not really truly on the equation sheet is the equation for centripetal force. And it's either m times AC or it is m times v squared over r, where we've just substituted v squared over r in for AC. The equivalent equation that is on here is the acceleration of a mass, and that is produced by a net force. So this is the same equation, except for now, because we're moving in a circle, this is AC is equal to our good friend mv squared over r because of what we do. So let's back this up and let's move on. Here we go. Let's go ahead and take a look at this diagram. So this diagram is of a car, and this car is turning to the left. We are looking at it from a helicopter view. So we're looking at it from the top down. Using arrows, I would love for you to show the direction of the following. I want you to show the tangential velocity of the car, the acceleration of the car, the centripetal acceleration, and the net force of the car. So you're going to actually draw 3 different lines. And if you want to put arrowheads on those, you can. There's a lot of different tools there that you can use. I would use the straight line tool if you want to make those straight lines. If you want to just use just the freehand tools, you can do that too. And that will work out really well. If you just came in, one of the things we would love for you to do is get on Pear Deck with us. And so I've put the link in the chat. If you want to go to the chat, you can see that. Click on that link, and then it will ask you to log in using Google, and you'll be set. And you won't have any trouble at all getting into that. So we would love for you to get in there if you don't mind. And go ahead, and we're going to have you draw 3 arrows on this diagram starting at the car. We want you to draw the tangential velocity, the acceleration of the car, and we're talking about centripetal acceleration here. And then the last thing to do is to draw the centripetal force of the car. So go ahead and take your time on those. Do remember that the tangential velocity is the velocity in a straight line. That is way different than omega, or the centripetal velocity, or the velocity, rotational velocity is what we typically call it. And remember that the acceleration of the car, this is the straight line acceleration or the centripetal acceleration, which is different than what we would do if we had the, let's see, it'd be different than if we had the angular acceleration. So these are still kind of straight line things we're looking at, a position of a car on a circle, and we're going to do the instantaneous velocity or tangential velocity, the acceleration, and the net force. All right, we've got some awesome answers here that I can see. I'm going to post some of these answers. Please know it will not show your name. It will just show that somebody has put something on. So this one's really good. I like this. They have the velocity going tangent to the circle. They have the acceleration pointing towards the center of the circle. And then finally, they have the force going towards the center of the circle. And so that one looks really good. This one, same type of thing. Very nice. Love this one. This one looks good. We do have an acceleration that's pointing in a little bit different direction, as you'll see here. And so we've got another one. I love this. We're talking about scalars and vectors here. Very good. Got another one. And so we've got a lot of really good diagrams. This one I think is really super impressive here. So let's take a look at what the actual answer is. And the actual answer for this one is the velocity is tangent to the circle, which means that if you think about this car going in just a circle, kind of like, whoops, what I'm doing here, then we know that the velocity is tangent to the circle. The acceleration will point towards the center of the circle, and then the force will also point in the same direction. Remember that mass is a scalar. We're going to take a scalar times a vector, and that gives us this force, and the force should be longer in terms of magnitude than the acceleration because it does include the mass of the object. So excellent job. Let's move on to the next one. So on this one, we want to know what keeps this truck when turning left or right from skidding. So this comes from the AP Physics 1 workbook. If you haven't used it before, you might want to do that. Just kind of take a look at some things if your teacher has access. I did put in the chat again the link to our good friend Pear Deck. And so if you want to get onto Pear Deck, all you'll have to do is click on that and it will allow you to go in and put your answers in so you can be super engaged in what we're doing. So if you don't mind, go ahead and circle whatever answer you think is correct. Seeing a lot of good answers here, so keep going. Remember, you learn the best when you make mistakes. So that is the best thing to do here. So keep going. I'm seeing a lot of good answers. Excellent. I love it. Seeing some great answers. Beautiful. Still seeing some really good answers here. Remember, it's okay if you just want to guess. I love it. So what we'll do this time is we're going to put all of the answers right on top of each other so you can see all the variety of answers that everybody's answering. So here we go. Check out all the answers. It looks like almost everything has been answered. I'm seeing inertia, momentum, force of static friction, and force of kinetic friction. So let's take a look at it a little bit differently. Let's look at it one at a time. So here we have somebody saying force of static friction. Here we've got a force of kinetic. Here's another force of static, force of kinetic, force of kinetic, force of kinetic, force of static. And then we've got several people saying inertia. All right, so we want to know what keeps it from skidding. So the best part of this is some of you have said inertia. Well, inertia allows the truck to keep moving because it's got that mass, and mass and inertia are about the same thing. So that is kind of correct, but it's not the best answer because, you know, just kind of take a look here. It says it's trying to keep it from skidding or from sliding. Momentum could also be part of that. However, momentum and inertia, remember, they are related because they both contain mass. But those are not the two things that keeps the truck from skidding. How about the difference between the force of static and the force of kinetic friction? Remember, kinetic friction is sliding friction. Sliding friction. So if you start to turn and you slide, you wouldn't be able to turn. You'd actually go straight through the intersection. So the best answer for this question is actually the, oops, that's not right. It's actually the force of static friction. So ignore the momentum. It should be the force of static friction. I think when we re-uploaded this, the answer must have been switched for just a second, but it should be the force of static friction. Why is it this force of static friction? I thought that this truck was moving. It is. Moving friction is sliding friction. That's really how you want to think about it. Static friction, if you think about a wheel, when a wheel touches the road, if the wheel makes contact and then lets go and does not slide, that's what we call static friction. So kind of a trick question there. All right. Here is our next question. This one is, we're looking at this truck from the front and it is turning to its right or our left. I would love for you to draw a free body diagram for the truck. I will give you a hint. There are three forces in this. There are three forces that you want to draw, and we will give you about 3 minutes to draw those. Make sure you draw them. Try to give relative lengths for things that are in equal directions or opposite directions, and label each one. So whenever you are ready, you can start going. Go ahead and just draw. You can do them freehand if you want to. And go ahead and label them, and that would be fantastic. So we're looking at the truck. It is on a horizontal flat road. And I'm starting to see some really good answers. I love what some of you are doing when you label the thing that is pointing straight down. I love what you're doing. That is beautiful. Excellent job. If you just came in, one of the things that you can do is there is a link in the chat to Pear Deck. And that Pear Deck link will allow you to get on to Pear Deck, and you can go ahead and join us here in Pear Deck, put some answers in, take some guesses, make some mistakes, and learn a little bit from those mistakes. Best way to learn. So I'm seeing a lot of great answers here. Remember, there should be 3 vectors for this one. So 3 forces. Most people are getting the 2 that are the most common. So we'll kind of check and see what other people say. Excellent. Looking good. Job, Andrew. Pratush, very good. Elizabeth. Excellent. Spandan, great. Vibra, good answer. So we've got some excellent answers here. Anna, good. Giesel, good. Job, Gabriella. I love it. All right. So let's look at some of these answers that you've given, because I really like a lot of these answers. Here's an answer from somebody. They're saying that the normal force is up, that the force due to gravity is down, and then they have the force of static friction, and it's pointing to the right. So there's one answer. Here's another answer that's very similar. Notice that they did, thank you so much for putting equality marks on. We know the normal force, and then here is what I'm super impressed by. I love the fact that you're doing mg, because mg will help you when you go to solve problems later on using dynamics. So excellent that these are equal and opposite and that they've used mg. You could also label this one fg or w, totally up to you. They have a force going to the left, and notice that, I love it. Beautiful job. They recognized whenever you label the centripetal force, we don't call it the centripetal force. It's actually comes from another force. So this one is the force of static friction is what they've put. So excellent job. So we've got another one with some of the other things that we did just in the last problem. So now we're going to look at this one. Here we've got a force of friction going to the right. So we're agreeing that we have up, down, and then either left or right. I love what they've put here in terms of Fn is equal to mg. That way we know for sure that those two are equal and opposite. Here's another one with friction to the left. Very good. Mg down. Here's another one, the force of friction down. Excellent. This is beautiful. Okay. So the correct answer is the one that has the force of friction going to our left. Because remember, the car is getting pushed in this direction from left to right. The car is pushing on the road to our right or to the car's left. In response, the force of friction pushes it towards the center of the circle, which would be to our left or to the driver's right. So here is that correct answer again. The force of friction is pointing to our left, and it is the force of static friction. So somebody even put in that it was static friction, which is phenomenal. Excellent job. Good job on that one, guys. This next one is a centripetal force apparatus. So the best way to explain this to you is this is a physics lab, and when you hook it up, you typically take a glass tube and a weight down on the bottom. Then we put like a rubber stopper, something that's a little less heavy, something that when we swing, if we accidentally hit somebody, it won't hurt that badly. And then it's all connected by a string. And so when we get this thing to start moving, it moves in a circle and it will actually lift things. So we would want to see that thing lifting as it goes through. As it lifts, it produces a force, and so we see that force. So I've got a video that kind of will show you what this looks like. So I'm going to open this video right where this person has got this thing swinging above their head. So I'm going to move this over so you can see it. All right, here we go. So here, oops, made this too big. So here is our person. They have the force apparatus, the centripetal force apparatus right here. And we don't need to hear them talk, but we can see it go around in a circle. And so this is really nice. As they spin this, it produces a force that pulls this mass up. Okay, and it pulls up because there is a force pulling that string towards the center. So excellent job, excellent, excellent. Let's go back, and we would love for you in the Pear Deck, there is a text tool. So you can use that text tool to answer the questions. Now, this first one says, write the physics equation below. And so I'm going to see what everybody writes, and then I'm going to help you with the physics equation here in just a second so you can kind of see what happens. What does the slope represent? And notice it just wants one word. So what is the slope represent? So it represents something that we can say in physics is pretty popular, and it's just one thing. So just one word. So I'm going to give you a little bit of time to go in. Excellent, Rachel. That is correct. I love these answers. You guys are doing great. Excellent. Gabriella, very good. That's second. Number 2 is correct. Very good. Yep. Gisel, you had it. You had it. That was the right answer. You were typing the right answer. Excellent. Go back and do it again. Perfect. Good, good, good. All right. I'm seeing some great answers here. Everybody's doing our equation here. That's very nice. I like it. I'm going to show you a little bit different way to do the equation. But you are doing awesome. Looks very nice. No, thank you. Good question, Gabriella. Thank you, Brianna, for answering that. Thank you, thank you. Seeing some great answers here, especially for the second part for question 2. Seeing some good physics equations also. Excellent. Viva, you are correct. Oh, you had the right answer, Viva. Leave it. Just that one word. That was awesome. So, Viva, what you had was perfect. That one word looks really good. All right, let's take a look at some of your answers and see what you're putting because they're looking really good. So this person did a great job here. They used more than one word. So we'll see if any of the words here are going to be right. I love what they did here in terms of showing a physics equation. They said FC is equal to mv squared over r plus 0. So they used y is equal to mx plus b, and that's kind of what I'm looking for. So I'll show you here in a second what we usually do. FC is equal to MAC. Perfect. Very, very, very good. And so I'm going to show you something new here. Acceleration is the key term for the second part for number 2. So very good. This is super close to what I would love to see. So that's very nice. Good. Excellent. So seeing lots of the right equation in terms of the equation. Every once in a while, you know what? If you don't get it right and you didn't put acceleration here, that's absolutely fine. Remember, we're just trying to go through and learn. So if you do it incorrectly, we will definitely help you out. Check this out. This is what I'm looking for. So I don't know who you are, but you are doing this perfectly. Excellent. Very nice. So this is really what I'm looking for the physics equation. So I'm going to take you over just so you can see what it's like. The physics equation does use, as somebody showed, y is equal to mx plus b. Here, we're not going to worry too much about our b value. It's probably pretty small compared to our slope, so it's probably not going to make much of a difference. In fact, you'll see that there's an equation up here at the top. This is y, force, is equal to mx. So m is our slope. X is what is on the x-axis, and then plus b. And notice that this b value is negative 0.000002. So it's super small. And because it's so small, we can ignore it. But when we write the physics equation, we start with whatever the label is on the y-axis, and that's equal to the slope. And here's our slope, 5.32. And it's either a Newton per kilogram or a meter per second squared. Then we're going to multiply that by whatever is on the x-axis. Now, why do we do it this way? Because for this graph, if I say that I increase the force to 100, if I increase the mass to 100, that makes it really easy to find out what the force is. If you notice in the right here, we've got our equation and we have our units. We notice that it's meter per second squared. Remember, meter per second squared does indicate that that is an acceleration. Here it is also the acceleration. So Newton per kilogram is really the gravitational field around the Earth, which is basically just acceleration. So that's excellent. You're going to notice that this person really did that same thing. But instead of putting the mass in, they just put m in, and that's okay too. So we're really looking to make sense out of these equations so that we see how they relate to our physics that we've been doing. Let's go ahead and take a look at this next. Let's look at this next thing. So in a quantitative translation question, that's where they're going to have you explain something and then calculate something. So we're going to treat this similar to that. Using your equation, we're going to calculate the mass of the swinging stopper that's up at the top. And so if you want to use a piece of paper or a whiteboard or something like that, that would be great. But the only thing you have to answer or put on here is just tell me what is the radius? I'm sorry. They want you to calculate the mass of that swinging stopper. My fault. So let's have you try to get the mass of that swinging stopper. So remember the equation we just used. It's basically just F equals ma. But we also saw that several people were putting m times v squared over r. So they were doing m times v squared over r. So here, if you need the radius, you can use it. You might not need it. But we're looking for the mass of the swinging stopper. Seeing some great work. People are actually doing the work right on here, which is perfect. Love it. So we know the hanging mass is pulling down, that weight hanger is pulling down with 22.2 newtons, which means that the centripetal force coming from the rubber stopper has to be the same. And if it's the same, then we know that they are equal and opposite. They're a Newton's third law pair, which means that we can find the mass of that rubber stopper just using our equation. F is equal to ma, or Fc is equal to mac. So Gabriella, you're doing great. You have everything you need, believe it or not. So what you have in green is perfect. You can just leave it because remember that is your acceleration. So now you just solve for m. Excellent job. Starting to see some really good answers here. Very, very, very nice. Do remember your units. Don't forget your units. Seeing some great math as we go through here. Do remember you can either use 9.8, 9.81, or 10 on the AP Physics 1 exam. So it doesn't matter what you want. So Spondan, what you want to do is, that's what we're trying to find, is not the weight. So you don't have to worry about the weight. We just need to know about the mass. We just need to know about the mass. And then if you know the mass, you would know what the weight is because you can just multiply that times 9.8 or times 10. So the equation is nice because it gives us what that force is going to be on it. All right, so let's take a look at what some of you answered, because it's always nice to kind of see some of the answers. So this person says it's 2.265. Here we've got another one, 2.22. This one, they're still thinking, which I love. This one, 4.17. Here we've got another 4.17 for mass. This person got a good start. At least they have the equation. That's a great thing. Here's another 4.2, 2.26. So let's take a look and see what the actual answer is. So this one is 4.2 or 4.17. And it's because the force that comes from the weight hanger is equal and opposite to the force coming from the rubber stopper. Now, because the rubber stopper is moving in a circle, it has centripetal force. So that is equal to the weight hanger. Somebody was asking about the weight or the mg of this. That would also take into account, but we typically don't look at that part of the problem because then we have a little bit of, we would say that we have a little bit of an angle here and the problem gets much more difficult at that point. So on an AP Physics 1 exam, they're going to say that this is straight across, which means that the force up and the force down would be the same. So the force, the lifting force would be equal to its weight. So the only force that's really being generated here that's a net force is the force towards the center. Okay, very good. So this time they want you to find the speed of the stopper. So we know the radius is 2.1. We know the mass of the stopper is 4.2. We know the centripetal force is 22.2. So this one should be a lot easier to do. You don't need the mass, by the way. So if you want to do this without the mass, you absolutely can. And you can find that pretty easily. So we'll give you just a couple minutes to do this. But you all are doing awesome. I'm seeing a lot of people participate in the Pear Deck, trying to get the right answers. So that's phenomenal. And there are two ways to do this. There's an easy way, and then there's a little bit more complicated way, but either way, you should get the same answer. You guys are doing great. Lots of great responses so far. I like it. Seeing a lot of thinking. Remember, the test isn't really a test of can you get the right answer? And they're not looking for just the right answer. They want to make sure that you understand kind of how to solve. So when you do these on the actual AP exam, you do want to show all your work. Always start with an equation in a problem like this. Fill everything in. Show whatever work you can. And then give the correct number answer with correct unit. A lot of times they won't give any points for the final answer in terms of the number, but they will give points for the equation and then filling that equation in correctly. So you folks are doing awesome. Good, good, good. Seeing a lot of good answers here. Sometimes we'll see these as multiple choice questions, and they will put every wrong answer that they can calculate in. So you just have to be really careful. But these are awesome answers. You're doing great. Beautiful job. Seeing a lot of great answers so far. Like it. Very nice. Beautiful. Somebody wanted to know if they could leave their answer in a fraction. You can do that. You'll make it easier on the readers, those of us that actually grade your exams every June, by putting it in a decimal format, because that's typically what we'll do. I always tell students it's kind of like if you get pulled over and you're speeding. If the police officer says, well, you were going 120 over 36.4, you're going to be really confused about how fast you're going until you get your calculator out. So a lot of times we want to go ahead and just put everything in terms of decimal point units. So I'm going to give you just another, I don't know, about a minute or so. Seeing a lot of good answers, though. Very nice. Excellent. Keep scrolling through answers here, seeing some correct answers, seeing some that are close. Some people are just making little mistakes, forgetting to do certain things. We'll go through that. It's how we learn it the best. Remember, we're looking for tangential speed. Yeah, absolutely. So if there's multiple parts, but you get the first part wrong. So for example, if you, let's say that the answer to part A is 5, for example, and you put 20. As long you won't get full credit for a part A, but in part B, if you take that 20 and put it into whatever equation you're using, from there on, they will assume that 20 is correct. So yes, you'll want to keep going. If you don't know a number answer for part A and you need it for part B, C, and D, make one up, because that way you'll still be able to get full credit for B, C, and D if you do those correct. We're looking for physics. It's not a math exam per se. It's really a physics understanding exam. So if you go through and you aren't sure how to answer the first part, throw an equation in there, put some numbers in that are on the problem, and get an answer. And then take that answer, even though it's an incorrect number answer, and use it for the rest of the problem. That is an awesome thing to do because we really want to give you points. And if you take the time to do that, it will come out great. All right, let's take a look at some answers here. So this person, 1.6 meters per second. Here's one that's 3.34. I love this. They erase their other work and then put their neat work down. I like it. I like it. Here's another 3.33, 3.33. So we're starting to see it. So 3.33. Now, you'll notice sometimes we forget to take the square root or we multiply instead of divide. So sometimes that happens too. But remember, if you show all your work, so for example, if this person accidentally, so they have the right equation here, and then let's say that when they did their math, they divided these two instead of multiplying, at least they have them in the right spot. So we can recognize that. So if this was 3 points, one for here, one for this, and one for the answer. If the answer is not correct, but you have the other two things correct, then you'll get 2 out of those 3 if this is worth points. So excellent job. The correct answer here is 3.33 meters per second. So excellent job. Here's the work I did. Now remember, there's 2 ways to do it. I use the net force. You don't have to do that. You could do what a lot of people did, and that was here, I'm going to back up one, just use v squared over r. Because remember, all we're looking for here is just the speed. You already know the acceleration from the slope, and you already know what the radius is because we gave it to you. So you don't even need to use the force equation. All right, let's take a look at this one. I love this question. So this is one that combines a little bit of dynamics, but with the circular motion principles. I want you to draw for, this is a roller coaster. And we have people that have gone down the first hill. They're coming up and we go over the top of the hill at position A. And then we go down, we hit position B, and then we go upside down at position C. What I would love for you to do is draw a free body diagram for position A, position B, just below the B, and for position C. So go ahead and draw a free body diagram. But I want you to be very careful that when you draw your arrows, you make them the correct size. So if your arrow up should be bigger than your arrow down, do that. If vice versa, do that. And then if there's anything that's consistent from left to right, you want those arrows to be the same. Go ahead and do that and label your arrows with whatever they are. And then we're going to take a look at these because this is a little bit more complex, especially at letter C. So we'll have you do it. We'll take a look at some of your answers. If you get it wrong, that is totally fine. You're learning and we're reviewing. So we want to see what you think. Starting to see a lot of great answers here. Excellent job. I like it. Very nice. Still seeing a lot of good answers. There is no friction here. I think that's one thing that we can kind of think about. Don't worry about friction at all. And you're all doing a great job here. I like it. Excellent. Again, thanks again for coming out and doing this with me. You're helping me too, because I love to see where you have a little bit of trouble, and then that helps me help my students. So excellent job. Letter A should be relatively easy. Letter B shouldn't be too bad. I think letter C throws some people, and that's okay too. I love these answers. Good, good, good. Job, Spondan. Excellent job, Giesel. Good, good, good. Gabriella, excellent. Elizabeth, great start. I love it. Pratouche, very nice. Remember on your diagrams, these are free body diagrams, so we only want forces. You want to be careful not to put anything in terms of velocity or acceleration. We just want forces. I did draw a big circle for letter A, so you could think about which way we would kind of think about that fictitious centripetal force. It's actually caused by something here, but we just want to make sure that we don't label anything FC. And don't forget, you want to be careful, leave all of the acceleration and velocity vectors out. We don't worry about those. We're just doing our forces. All right, I'm seeing some awesome answers. All right, let's take a look at some of these answers. Remember, this one's a little bit more difficult, but did a good job. We do know that mg always points straight down. So because Earth is always pulling that roller coaster down, no matter whether it's going up, down, left, or right, it's always going to pull it straight down. And those arrows should be the same size, which is really good. If we look at the top one, you'll notice that Fn does point up. That's correct. Fn points up here. But right here, we have Fn pointing down, which is 100% correct. The only thing that I would change on this one is we want to make this Fn shorter than our mg because most likely you feel like you weigh less here. And then we want this Fn to be really long because we feel like we weigh more at B. For C, we're not really sure because we don't know how fast we're going. But I love this little comment that this person made. Surfaces are touching, so Fn is perpendicular. Very good. That is super important to recognize. A lot of people don't see that. Excellent. So here's another beautiful answer. I love it. Here's another one that's really good. So we want to look at this one. You'll notice that this Fn is shorter than this one. When you go over the top of a hill, you usually go wee because you feel light. And then when you go down at the bottom of this hill, you go ugh because you feel very heavy. We're not too sure about this one because we have to kind of know what speed we have so we can kind of figure out whether we have much of a normal force or not. So that's really important. So just looking through, you can kind of see how everybody did. So you don't know, huh? You're right. You don't include the centripetal acceleration in these diagrams because remember, these are free body diagrams or force diagrams. So because acceleration is included in the force, we don't need to put the accelerations in. Another really good answer. They've got a little extra arrow here, so they'll erase that, and then that'll make it 100% correct. But these all look really good, so just be really careful as you go through. I do have the correct answer on here. It does look like this. The only one that could have some different things on it is right here. That Fn could be shorter or longer depending on how fast you're moving through that circle. All right, so what we're going to do here is I did ask another question about how heavy somebody would feel. We don't have a lot of time left, so I want to make sure that we go ahead and move on to a little bit of universal gravitation. So here's the complete solution for that problem at letter B. If we move on to the next one, you're going to see this is a question about a free body diagram. And this is for a flying pig or a flying toy that's going in a circle. So I gave you some answers for that, as well as asked you to solve some things. So I'm going to go ahead and give you those too. When we're done with this presentation, I'm going to give you a link so that you have everything in the presentation so you can go back and study or try to do some of these things we just didn't have time for. I'm always going to include some extra stuff for you. All right, so what's important about universal gravitation? One of the things that's super important is to recognize that on the equation sheet, there are things that you're going to need, and they're at the top of the equation sheet. So I've put them here, but I want to show you exactly where they are. If you go to the first page of the equation sheet, there's a lot of useful information. The big thing that we need for universal gravitation is this constant, which is super small because gravity is actually a very weak force. It takes extremely large objects to give just a little bit of force. So if you think about how big the Earth is, it creates a force that doesn't crush us. We just kind of have our own weight. It also gives you the value for the acceleration due to gravity. Remember, you can also use 10 for this. So it's super important that you see that. The other equations are on the equation sheet. That includes the absolute value for the force of gravity or the gravitational attraction between two things. This could be between you and a classmate. It could be between you and the Earth. It could be between two planets. So we can use this in a lot of different places. This is typically the one that we think about for Earth, and that's where our 9.8 comes from. But if you went to the moon, this G would be 1.6 instead of 9.8. And if you went to Jupiter, it would be a lot bigger because there is much more mass in Jupiter. This is the energy, or the energy between two objects. So two small objects won't have much energy, but two big objects absolutely do. So those are some of the equations that you'll see. R is radius, and you'll see radius in a couple of equations. One of them is in the force due to gravity. The other one is in the centripetal force. And when we're dealing with something that is orbiting something else, so for example, we're looking at the Earth. If I know I have a satellite and it's at 200 kilometers above the Earth, we also have to add the radius of the Earth to that. So they have to give you those numbers if you're going to solve a problem like that. So that radius is actually the radius of the Earth, or the radius of whatever planet it is, plus your altitude, which is 8h. So just another really important thing for you to recognize. For this one, they want you to solve for the centripetal force and for the force due to gravity. Well, we don't have a lot of time for you to work through that. So what we'll do is we'll just take a look at the answer. So here, this kind of got covered up. This one is mv squared over r, and then that gives you your centripetal force. And then your centripetal force is about 4 million or so newtons. If we look at the force due to gravity between this shuttle and the Earth, you'll notice that it's very similar, okay? It's a little bit less than what we would do if we had the centripetal force, but they are very, very, very close. So we wanted you to see that. We can also figure out how fast a satellite is moving as it travels around the Earth, and we can use those same type of equations. So I'm going to use both of these equations. I'm going to set them equal to each other, because I know that that force due to gravity is the same as the centripetal force pulling that satellite in. And if I set them equal to each other, I can actually solve for an equation for the speed of an orbiting body. The next thing is just looking at how fast the satellite's actually traveling. So we put all the numbers in, and this is typical for a orbiting body. It's about 7,769 meters per second, which is really, really, really quick. The last slide here is just to make sure that you know that you can keep this conversation going in Discord. And we are almost done, but here's what we're going to do. I'm going to start Gimkit. And Gimkit's a fun little game that we've been playing. It's very similar to the trivia that you guys can do. So if you ever want to go through some just questions and play trivia, this is a great way to, that is a great way to do it, is to go to trivia night. So you want to make sure you do that. And then the other thing that we're going to do here is we're just going to play for 7 minutes. Actually, let's do 6, because we're going to have to get everybody on. If you go to the link that we have here, so I'm going to copy the link. I'll put it in the chat. If you just click on that and just put in your first name or a pseudonym. So if you want to call yourself Batman, you can do that. or you can call yourself Wonder Woman or whatever you would like there. Just keep it clean. Then we'll play this little game. And so if you click on the link, or you can go to gimkit.com/live and enter the code 34482, then we will play this just a little bit. It's got some pretty nice basic questions for you to do. And while you're doing the game, I will go ahead and create the link so that you can get the presentation. So I'm going to end this. So we'll give you about 30 more seconds or so here to get on. I love it. Wonder Woman, beautiful. Excellent job. All right, we're going to go ahead and start the game here. So I'm going to get it going, and we are off. I have the link to the presentation too. I'll put that in the chat. Excellent job. Doing really well here. Got Gisel, Greta, Spandan, and Marmar. So far at the top. PN jumps to the top. You'll notice that there's a shop button. So if you go shopping, you can actually, once you have enough money, you can buy power-ups, which means you can get more money per question. So far doing an awesome job on this. Just some basic things about centripetal motion. Love seeing you jump up and down here. This is good. Folks are doing awesome. Keep going. Alexander did upgrade some money here. Like it. Got about 4.5 minutes. Such a good way to review. If you can find things like this. I know Quizlet has some things like this that you can do. Got a little going back and forth here between Spandan and Marmar. Got Viva coming up. Up to $348, doing awesome. Do you know there's a little bit of a delay? So when I say there's so much time left, you know that there's already a lot less than that, which is fine. Doing great. And we are now at 3 minutes. Got Viva. Spandan just took the lead again. Rachel just upgraded her stuff. Good job. It's looking really good here. All doing great. Excellent job. Wonder Woman just upgraded. That's awesome. Got people moving up again. Get those power ups really helps. Got 2 minutes. 2. Doing excellent. Spondon's back up at the top, still followed by Marmar, but we've got your name in there. PN, Viva, kind of, yep, there we go. Go switch again. Excellent. Coming down to about a minute left. Guys are doing awesome. Got multipliers and bonuses here. Streak bonuses getting upgraded. Money per question. Very nice. Got about 35 seconds left. You can see some people really starting to move pretty quick here. Guys are doing great. 25 seconds on my end. Doing awesome. Nice job. I like it. Mega even changed the background for their name. I like it. And we've got 4, 3, 2, 1 seconds. Time is up. Beautiful job. Your name, $350. Alexandra, $539. And Spondon up at the top with $957. Hey, I appreciate you guys. Thank you so much for coming out and learning with Fiveable today. Like we said, if you click on the link in the chat, you'll see the one that has https app.peardeck.com. That is your copy in Google Doc format of what we did today. Do remember the one answer that said momentum was not correct. That one should have been static friction. But other than that, everything else should be correct. I'll go back and fix that so that it's good. You all have an awesome day. We will see you again on Friday. Don't forget, we're going to do it again. And we'll play Gimkit a little bit again. Remember, that one is on energy. So thanks again, guys. We will talk to you all later. And I think that is the end of our time today. So thanks again. See you all later. Have an excellent day. Go do some physics.